So there is a lot of mathematical formulas here, but I will try to make it very, very simple for you. So remember I said that the effective reproduction number is just the basic reproduction number multiplied by the proportion of those who are susceptible. And this proportion here can be written in another way. The proportion of susceptible is, because it's a proportion, the maximum is 1. It is 1 minus those who are immune in the community. So we have this formula here. So for an infection to take off, the reproductive number here, the effective reproductive number, should be more than 1. But if we want the infection, we want to control the infection, we should make sure that the reproductive number here is less than 1. So this here, which is our effective reproduction number, should be less than 1 if we need to control the epidemic. So from this formula here, we can deduct what we call the herd immunity threshold, which is the smallest fraction of people we need to immunize or we need to give vaccine to in order to have a good effect for the vaccination. So the herd immunity threshold is just R0 minus 1 divided by R0. Let's see some examples here to make it more realistic. For example, in this scenario here, R0 is 4. 4 means that you can transmit infection to 4 people. If no one is immunized, so F is 0, no one has the infection, this means that the effective reproduction number equals the basic reproduction number in that scenario. And 4 people would be infected in this case. But if 25% of the population here is immunized, what happened? Our effective reproduction number becomes 3. So if we vaccinate 25%, even if our R0 is 4, the person here can transmit the infection only to 3 people here. Let's increase the vaccination to 50%. When we increase to 50%, it can contaminate only 2. And when we increase to 75%, it can transmit infection to only 1 person. So this means that if we give more than 75% as a vaccination coverage, we will stop the transmission with an R0 of 4. Let's take a very small R0. Here, it's 1.2. With 1.2, if no one is vaccinated, F is 0, it can contaminate 1.2 person. This is, that means that the infection can go on. But if we vaccinate 25% of people, our effective reproduction number becomes less than 1. And we can go on and on. But what does it tell us here? It tells us that if R0 is small, it takes only a small fraction of people to be vaccinated in order to be able to control the epidemic. So this is very important. Any vaccination or immunization programs that consider that, how many children should we vaccinate? How many adults or elderly should receive flu vaccine, for example? We need to know the R naught of the specific infectious disease in order to be able to estimate the number of people who should receive the vaccine. And as you can see, different diseases have different estimated R naught. For example, for diphtheria, it's 6 to 7, and it has also different estimated serial interval. You remember, we've seen it in the beginning of this lecture. Measles has a very high R naught, means that measles can transmit very effectively, because one person with measles can give to 12 up to 18 more other people, compared, for example, to influenza, which can give to 2 or 4 people. This also means that we need a higher rate of vaccination for measles compared to rate of vaccination for influenza. Measles is much higher because the R naught for measles is much higher compared to that of influenza. So there is obviously a relationship between R naught and how many people should we vaccinate. As R naught increases, the number of people we should vaccinate also increase. But at a certain point, maybe from 7 here, it's reached a plateau. So even any further increase in the R naught is not followed by a big increase in the vaccination rate or coverage. But the take-home message is that the vaccination coverage is based on the value of R naught. Bigger R naught means higher vaccination coverage. Lower R naught means lower vaccination coverage. Another message is that you don't need to vaccinate everybody, because those who receive vaccination, those who are immunized, can indirectly protect those who are not immunized. And this is what we call herd immunity.